Well, thank you very much for the invitation. It's a great pleasure to make a presentation. It will be an even greater pleasure to be physically present somewhere else than Cambridge. But I'm afraid in these days that doesn't seem to be possible. In a certain way, what I'm about to tell you about is a product of being locked down and seeing virtually nobody to restrain my imagination for the last 18 months. So what I want to discuss is the information paradox and a possible way of getting around it. As we all know, the basic idea is that if you have gravitational collapse to form a black hole, and it undergoes Hawking evaporation, then it's generally believed that there should be a unitary map between an initial surface, sigma I, and a final surface, sigma F. But of course, the basic problem is that if you look at the Penrose diagram that's explaining this, then you'll see that there is a horizon that forms. Inside the horizon, nothing can get out, at least classically. The collapsing matter falls into the singularity and disappears from the space-time. And so it's rather hard to see how the information could fail to be lost. That's assuming that the usual laws of physics apply. And so clearly what has got to happen is that something dramatic has got to change if you're going to be able to understand how there is a unitary map from sigma I to sigma F. So that's the basic picture that one has. Now, of course, the picture here is for the Schwarzschild metric, and it illustrates Oppenheimer-Snyder collapse. But perhaps one shouldn't be too worried about the fact that it doesn't look like the Kerr space-time. And the reason for that is that if you look at the Kerr metric, then its causal structure is somewhat different. There is an inner horizon, but the inner horizon is known to be unstable and is presumed to form a singularity, which would either be null or space-like. And so this picture that you have would seem to be a sort of fairly generic kind of picture that you get, at least if you think traditionally about what happens in gravitational collapse. So it would appear that unitary evolution between sigma I and sigma F is impossible. So let's try to see if we can understand precisely what is making it difficult. Anything that passes through the event horizon will eventually reach the singularity. And since singularities are the boundary of space-time, anything arriving there will just simply have left the space-time and it will have disappeared. You might think that perhaps quantum mechanics gets you out of that, but in linearized theory, if you look at the Tucholsky equation, you'll discover that in the Schwarzschild metric, for example, wave functions do not vanish at the singularity. In fact, in the case of scalar waves, the wave functions actually blow up because there's a logarithmic singularity there in the solutions. The probability current is typically non-zero, and so you're inclined to think that there is going to be no change quantum mechanically. And that's really a reflection of the same kind of thing that happens to the inner horizon in Kerr. The solutions to the wave equation, the Tucholsky equation, blow up on the inner horizon, and that's the reason that one thinks that there is an instability. So that's the first problem. It's basically telling you that stuff that falls into the black hole, whether it be quantum mechanical in nature or whether it's classical, just simply leaves the space-time. And so causality, in its usual form, seems to imply that once it's gone, and that's it. There is a second problem, which is a little more technical, and that concerns the entropy of the black hole and the Hawking radiation. So here is a sketch of what happens. This black line here and here is going to be the horizon. Typically what will happen is there will be some Hawking radiation, and let's suppose that this is labeled by the state R. its entropy will be S sub R. Similarly, there will be an entropy of the black hole, S sub H. Let's ask ourselves what happens if you look at the evolution of this system for a little bit. A typical example will be the pair production of one Hawking quantum. That is to say that there will be a particle X, which escapes to infinity, a particle X bar, which falls into the black hole. That will be the antiparticle pair of X. And because this is a pair production event, the joint entropy of X and X bar will be equal to 0. It's a pure state. Then, a little later, the joint entropy of the previous Hawking radiation and X, we can call SRX, the joint entropy of the black hole after absorbing this antiparticle will be S of X, HX bar. So there's a sort of system there, but what you expect is that if it is really the case that unitarity is preserved in black hole evaporation, you expect the entropy of the black hole to decrease. You expect the entropy of the total Hawking radiation to decrease. That means that SRX had better be less than SR, and SHX bar better be less than SH. The black hole entropy is presumably a coarse-grained entropy, A over 4. And so this is the kind of situation that is described by the picture. Assuming that the evaporation really is unitary, you have these inequalities on the various states of the system in terms of what their entropy actually is. So let's ask ourselves what happens in detail there. What happens to the entropy? Well, let's suppose that the initial and final states are pure. The entropy of the pair XX bar vanishes, but the entropy of X and X bar itself separately will not generally be 0. And then we know that the Hawking evaporation is expected to decrease the entropy, both of the hole and of the radiation. And then we can use some simple rules of quantum mechanics and statistical physics to deduce the strong additivity of entropy. If you have any tripartite system, in this particular case, I picked the radiation before and after the emission of one quantum. SR is before, SRX is afterwards. S of X bar is of course 0 because the particle-antiparticle pair is in a pure state. And then on general grounds, one has this inequality. But since S of X bar is equal to 0, you get the inequality that SRX minus SR minus X bar is positive. But since SRX is less than SR and all entropies are positive, there is a contradiction between the rules, usual rules that lead to strong additivity of entropy and the evaporation process. So whatever you do, you've got to be able to explain how that inequality fails in this particular case. We've discovered that if you just apply the usual rules, things do not work. And so one is led to contemplate what happens in quantum gravity, as opposed to just thinking about putting classical or semi-classical fields on a fixed gravitational background. So let's have a brief revision of canonical gravity. In canonical gravity, one assumes that space-time is foliated by a time coordinate, and you can split space and time off into two separate things. You can write the metric in the form minus alpha squared dt squared. Alpha is going to be the lapse function. And then there will be a spatial metric, gamma ij. So the line element in total is gamma ij dxi plus beta I dt, dxj plus beta j dt. Beta I is usually called the shift, and gamma ij is the spatial metric. In what follows, I'm just going to look at the gravitational field and not extra fields added into gravity, but they, as far as I can tell, don't make a significant difference, except possibly in the case of having master scalars, which I'm going to leave out of this discussion. So the 10 components of the gravitational field are turned into the spatial metric, which has 6 components, beta I, 3, and alpha, just 1. And as we all know, gravitation is a gauge theory, and so one should expect some of these variables to be redundant. Alpha and beta I have no conjugate momenta to them, and therefore they are pure gauge. So that reduces the number of degrees of freedom by 4. And of course, having done that, you can then fix the gauge. And so that tells you there are really only 2 degrees of freedom per space-time point. 10 minus 4 gives you 2. So that is the correct counting. The embedding of the spatial metric into the space-time is described by the second fundamental form. And you can write that in the terms of this decomposition as 1 over 2 alpha times di beta j plus dj beta I minus the time derivative of the spatial metric. di here is going to be the covariant derivative constructed from the spatial metric gamma ij, and all of my Latin indices I, J, K, L, etc. will be raised and lowered using the 3 metric gamma ij. It's fairly easy to work out what the momentum conjugate to gamma ij is, and it can be written in terms of the second fundamental form. And notice that it is a tensor density, not a tensor. So the dynamics of the theory really boil down to just a knowledge of pi and gamma ij. Alpha and beta you can fix by choosing appropriate gauge conditions. Often the Gaussian gauge alpha equals 1, beta is equal to 0 is chosen, but that's not really necessary for what we're going to do here. The constraints of the theory is all that is left in canonical gravity. There are 2 of them. There is a diffeomorphism constraint, which says that the momentum is divergence free, and there is a Hamiltonian constraint, H, which basically looks a little bit like a Schrödinger operator. There is going to be something which looks like momentum squared, and then there's something that looks a bit like a potential, which is the Ricci scalar of the 3-dimensional metric gamma. So if you think of this as being a bit like a kinetic term, then G would be an inverse metric. And in fact, Gij,Kl is the contravariant metric on the space of all 3 metrics at a fixed point in space. Since pi ij is a symmetric tensor density, it's going to have 6 components. And so you can think of these ij's and k's as pairs, and this really is a 6 by 6 metric on the space of all 3 metrics, that is the space of all symmetric tensors in dimension 3. And if you calculate what G is in terms of the 3-dimensional metric, it's this slightly cumbersome looking expression. But what you can see from this is that it has got 5 space-like directions. Space-like should be inverted commas for the simple reason that it's not space-like, it's just simply a positive direction. And there is 1 time-like direction, which corresponds to conformal transformations. So if you performed a conformal transformation on gamma, that's going to be the thing which gives rise to moving in a time-like direction. So this is a sort of perhaps a Schrödinger-like thing. But of course, there is no time involved in it. It's not h equals some time derivative, it's h equals 0, and that's a consequence of general coordinate transformations. The fact that time disappears from expressions like this gives rise to considerable debate in various quarters. we're not really interested in that here. What we're really interested in is not so much the three metric at each point in space itself, but really the three geometries. The space of all metrics modulo diffeomorphisms is the space of all three geometries and is referred to as superspace. Not to be confused, of course, with what happens in supersymmetry. This superspace predates that. If you're asking about classical solutions to the Einstein equations, then they are curves in superspace. One way to think about that is you can say, well, if you fix time, what happens? Well, you have a three geometry, provided you fixed alpha and beta. If you ask what happens a little bit later, well, it'll be a different three geometry. And so you can see that that's what happens. Classical solutions represent some kind of curve in superspace. The fact that you can have conformal transformations, which lead to a change in the determinant of gamma, as gamma goes to zero, you will discover some kind of singularity. This kind of singularity could be one of three kinds. It could be a signal of topology change, or it could be a space-time curvature singularity, or it could just be bad coordinates. However, this is something that one should be rather careful of, and indeed, at some level, you should regard this as a sort of avatar of the singularity theorems in classical general relativity. If you forget about the conformal factors and just simply think about the geometry of space with a conformal factor fixed, then you discover that the 5 remaining degrees of freedom of gamma ij are the symmetric space SL3R, quotiented by SO3. And so that tells you that since that's a non-singular space, there are no singularities associated with this symmetric space, then that tells you that singularities are always associated with conformal motions which are degenerate. Thing which is not quite so obvious, but is really, if you think about it, it's not so obscure. Each point in superspace represents a three geometry. That's something which is rather crucial to what comes next. Lastly, a terminology, a truncation of superspace is usually referred to as mini-superspace. Well, so far what we've done is all classical. Let's ask ourselves about what happens if you try to do things quantum mechanically. The usual quantization procedure seems to be the right thing to do, so it's just an infinite number of copies of the Heisenberg group at each point in space. You replace the momentum by minus I times the functional derivative with respect to the three metric. So that's the first step. That's an operator, basically turning things into operators. Then what you want to do is to think of a wave function, psi. That's going to be a function now of the three geometry. And of course, if you fix the gauge, that will correspond to some particular set of gammas. If you want psi to be gauge invariant, let's say it does not depend on what coordinate system you choose for the three geometries. And the thing which guarantees that psi is a gauge invariant thing, and hence a functional of the three geometries rather than just the metrics, is guaranteed by the diffeomorphism constraint. And so that's imposed by saying that chi I acting on psi is equal to 0. Then all that is left is that h psi is equal to 0, the remaining constraint being just the Hamiltonian constraint. And that's usually known as the Wheeler-DeWitt equation, and it's all that's left of the Einstein equations when you've done that. So h psi looks a little bit like a Schrödinger equation, but with no time dependence in it. Another way of thinking about this is to represent psi as a path integral. You can do that, the path integral over the space of all metrics using the Einstein action that have the space geometry gamma as a single boundary will reproduce a solution to the Wheeler-DeWitt equation. And so that leads you to the idea that psi of G represents the probability amplitude for the 3 geometry 3G. So we have some intuitive understanding of what the Wheeler-DeWitt wave function means, either from the path integral or from solving the Wheeler-DeWitt equation. Now let's go back to gravitational collapse and black holes. One thing which is really kind of obvious is that in realistic gravitational collapse, it's not going to be spherically symmetric. There'll be all kinds of inhomogeneities, and a study of how one approaches singularities was carried out really over a period of, well, since the early 1960s by Khalatnikov and Lifshitz, and latterly joined by Belinskii. It showed that the approach to a space-time singularity is chaotic. Space gets split up into various separate domains, and each domain behaves more or less independently. If you just look at the geometry of a single domain, then it looks a little bit like the Kastner universe. Let's look at the Kastner metric for a little bit. It's almost like flat space, except that there's some time dependence in front of the 3 spatial coordinates. So the Kastner metric is minus dt squared, and I'm going to suppose that there is a singularity at t equals 0, and that you approach t0 from below. Then you discover that there are various powers in front of dx squared, dy squared, and dz squared, and those powers will be t0 minus t to the power 2p1 or 2 or 3. The Einstein equations tell you that p1 plus p2 plus p3 is equal to 1, and p1 squared plus p2 squared plus p3 squared is equal to 1. This equal sign here should be a plus. I'm sorry about that. And that really tells you that there's contraction in 2 directions and expansion in 1 direction, but in such a way that the volume of each domain looks like t0 minus t. There's some numerical factor that goes with that. So this, in a certain sense, is an example of a mini superspace. What Belinskii, Khalatnikov, and Lifshitz showed is that there are domains where the metric looks like this. But it's not true for all times. Kastner evolution is turned into a series of epochs, and there is a transition between different epochs in which the parameters pi change, and the principal directions in which the contraction or expansion is going on also change. There is a simple way of describing this, and this was worked out by Henno and Damour and Nikolai. They're basically saying that each individual domain can be thought of as being equivalent to a geodesic in this metric here. There should be no plus sign here. It should be dv squared. Just minus d rho squared plus rho squared over v squared du squared plus dv squared. As rho goes to infinity, this metric is singular. If you look at rho equals constant, you get du squared plus dv squared over v squared, and that you will recognize as being the Lobachevsky plane, a 2-dimensional space of constant negative curvature. The behavior of the space-time is a null geodesic in this metric. If you think about this, each point in this space represents a geometry. This is not the geometry of space. Each point in this is itself a geometry. That's the nature of superspace. Each point in superspace, or each point in mini-superspace, represents a geometry. And here, the null geodesics corresponds to how that geometry evolves in time, at least classically. So you can see that as rho goes to infinity, this thing is singular, and so that's the kind of place where one should be thinking about what happens quantum mechanically. This, of course, is an entirely classical calculation. If it was all of the hyperbolic plane, the Lobachevsky plane, then, of course, it would be Kasner evolution all the time. This is just another way of rewriting that. But it's not all of the Lobachevsky plane. It's a particular region F in the UV plane, and different Kasner epochs occur when the geodesic bounces off the walls at F. So one way of looking at this is to say, well, I'm going to say, look at a null geodesic. If you know what U and V are doing, then you know what rho is doing because it's null. So all you really need to do is look at what happens as this thing evolves in the UV plane. So here is a picture of the UV plane. This is a unit circle in the UV plane. And the allowed region that the space-time is allowed to involve in is this shaded region, F. It's exterior to the unit circle. It's bounded here by U equals a half, and it goes all the way up to infinity. And the motion of the part of the geometry corresponds to null geodesics, so they look like straight lines here. They bounce off the walls here in this particular way. So this line here is a particular Kasner epoch. This is a different Kasner epoch, and the different epochs correspond to the bounces off the walls here and here, and so forth. Of course, you're quite likely to recognize this as being half of the fundamental region of SL2Z. What this is actually is the fundamental region of GL2Z, which of course is closely related to SL2Z. So F is the fundamental domain of that group. Each Kasner epoch corresponds to an element of GL2Z, and each bounce is represented by an element of the Weil group of GL2Z, which is the hyperbolic Kac-Moody group A1++. It is fortunate that numerical studies of gravitational collapse support this basic picture where you have chaos emerging. Well, that's the classical picture. What happens quantum mechanically? Well, quantum mechanically, you're just going to have some truncated version of the Wheeler-DeWitt equation, which boils down to the equation at the top here. So it's just some nice partial differential equation. And you have to restrict the UV variables to the domain F. That requires you to put boundary conditions on psi, and that's simply that psi is equal to 0 on the walls of F. That's because classically what happens is that the geometry bounces off the walls, and you know how to deal with rigid walls in ordinary quantum mechanics. It corresponds to having an infinite potential, tells you that the wave function has got to be 0. Solving this equation is a complicated matter that involves all kinds of terrible functions in the domain F, but fortunately a number of theorists have explored this quite thoroughly. Then what you discover is that the modulus of psi looks like rho to the minus a half as rho goes to infinity. So what that's telling you is that the amplitude for geometries that are becoming singular is going to 0. Of course, there's no reason to suppose far away from what is classically would be a singularity that semi-classical reasoning doesn't work. It's just simply that as you get close to the singularity, the BKL regime takes over, and you discover that this property of the wave function tells you that singular geometries do not happen. Nevertheless, it is the case that the general picture that we had right at the beginning is sort of telling you what's happening. So the question is, what should you do about the singularity? The fact that the wave function vanishes there is basically telling you that there is a potential resolution of the black hole information paradox that you get by setting the density matrix on a surface close to the singularity to be equal to 0. That tells you that really there is a boundary condition in the future which is stopping things escaping from the space-time. What that basically says is that causality in its usual form should be expected not to work inside the black hole. And a consequence of that is that the derivation of the subadditivity of entropy does not hold under these conditions. And that is rather fortunate because you have dealt with the two problems that we outlined to start with. Now, you might say that setting boundary conditions in the future is something that you're not supposed to do. And indeed, it does seem like a rather radical suggestion. Nevertheless, Aharonov, Bergman, and Leibovitz, some time ago, motivated by making quantum mechanics time symmetric, did make a proposal along these lines, that there would be conditions under which you could set boundary conditions in the future. In the quantum information community, this is known as post-selection, and there have been some experiments to test these ideas, although clearly not in the case of black hole physics. So this is a suggestion as to how to get round the information paradox. There are various things that, of course, one should do as a consequence. You want to know if there are any tests of these ideas. Well, the answer is, of course, to find a black hole that evaporates and show that unitarity is preserved, but that doesn't seem so easy. A different kind of test is that if you thought that this created strange behavior outside the horizon, it might be observable, or it might rule out these ideas. One doesn't know. And of course, this doesn't answer how information escapes from the black hole. It just tells you that information is not lost. So there are plenty of things that there are to do to follow up on this idea. And of course, hopefully, that will be explored in the near future. One other thing I should say is that about almost 20 years ago, Horowitz and Maldacena also made the suggestion that perhaps one should be putting boundary conditions in the future in order to solve the information paradox, although they didn't have any specific reason for putting any particular condition on the density matrix in the future. Here you do see one. So that's an idea that needs to be followed up and completes everything that I have to say for today. Thank you for listening.
Thank you very much for the very nice talk. Okay, so the now session is open for questions and comments. Okay, I see one person in the audience. Okay, Che-Yu Chen. Okay, can you speak?
Yes. So thank you very much for the nice talk. So I have a question. So in this approach, it seems that it strongly relies on the assumption that near the singularity, the space-time should be described by the Kastner 1. So my question is, how close to the singularity can we really make this assumption? Is it necessary to be Planck scale?
Oh, that's a very interesting question. The answer is I do not know. So the version of the question that I've considered but don't really know the answer to at the moment is, where does BKL behavior set in, and how large are the actual domains in question? So to answer that question, what you have to do is to compute the corrections to BKL. That means that you have to look at how, well, let's see. Essentially, it means you compute the potential. So the potential in the BKL idealization is that the walls have infinite potential, and that's why you get to zero. And that's something which holds asymptotically as you get close to the singularity. But in practice, the potential is just increasing as you get closer to the singularity. Of course, it becomes infinite at the singularity. And the question is, how close, how rapidly does the potential rise? And how does that make the various domains become causally disconnected? And the answer to that is, I don't know, but it is something that is being looked at right now.
Okay, thank you very much.
I should say that, of course, one could try to tackle that kind of problem numerically, but I haven't been doing that, but I think I might be able to persuade someone to try.
Okay, thanks.
Which will be easier.
Yeah.
Daniel, you want to talk?
Yes, if I may.
Yes.
Malcolm, can you please comment a bit more on on the third statement that strong subadditivity of entropy doesn't hold under these conditions? So in practical terms, it looks that you change the rule according to which you prescribe the marginals of your overall density matrix.
Right.
And then, of course, it's not going to. And then, of course, the usual subadditivity doesn't work. So basically, you are changing the rules of quantum mechanics.
Yes, that's exactly correct. Well, I'm following what Aharonov.
I'm not criticizing. I'm just trying to figure out the logical sequence.
Yes, what you say is absolutely correct. You are changing the rules of quantum mechanics, and the only way in which you could understand perform sensible interpretation under these conditions is to use consistent histories. And in fact, that's what Aharonov, Bergman, and Leibowitz did, although they didn't know that at the time. So what you really have to do, and it's sort of kind of obvious if you think about it. Suppose, for example, you're interested in a system in which you're going to look at how a density matrix evolves. Then traditionally what you do is you would use the Keldysh-Schwinger approach and write the path integral that way. But if you think about that, you will realize that in the future, they implicitly impose the condition that you're looking at a pure state. That's because the forwards and the backwards paths in the path integral converge there. But if you thought that all the rules of physics should be time reversal invariant, what you would do is to replace that pure state by a final state density matrix to mirror the initial state density matrix. And that's essentially what they did. But then you ask, what do observations correspond to? Well, they correspond to projections onto the Hilbert space. And then you need, of course, to decide what those projections are. In the case of gravity, this was explored, although not in as much depth as one would like, by Gell-Mann and Hartle. And what they did was great, but they didn't go far enough. And the real reason for that is that you don't know what the conditions are on the projection operators. If you were non-relativistic, you could follow what von Neumann and Birkhoff did and invent a form of quantum logic which stops you having projections which don't commute at the same time. However, what they did was entirely non-relativistic, and there ought to be some relativistic version of that, which I don't seem to know anything about. Chris Eischen tried to explore that issue some time ago, but I find his work to be rather impenetrable at the moment. Perhaps I'll understand it later.
Thank you.
Okay, so actually I have a question. So
Sure.
Yes, so at some point I think you mentioned that you don't want to change the semi-classical gravity up to Planck scale, but I think you do before reaching the horizon. Because,
no, I didn't say at the Planck scale. I said somewhere.
Okay, yeah, I think you already changed the semi-classical gravity before reaching horizon. Let me explain this. So you put the wave function to be 0 on the singularity. So if you compute the Klein-Goldnick norm, I mean, I think for the Wheeler-DeWitt equation, we can define kind of triangular norm, and it is, I mean, preserved. And so if you compute a triangular norm on the singularity, it is 0 because wave function is 0.
Okay.
Then which means that the
understand.
triangular norm on the horizon is 0, right?
Yes, I see what you mean. What
Yeah.
you're basically saying is that putting a future boundary condition on the horizon has an effect, sorry, on the singularity has an effect on the horizon. That's
think so.
absolutely right. And where that has to be the case, otherwise the information could never escape.
Right. Yes. Yes. So how I mean, so we need to, I mean, introduce new physics before
Yes.
reaching horizon scale.
Yes, but you knew that before you well, you knew that 40 years ago almost.
Okay,
That you have to introduce some new physics, otherwise there is no way in which you're going to resolve the issue.
Sure. Do you know how?
All I know is what I've said.
I see. Yes. Yeah, thank you.
Maybe that's enough. I don't know.
Yep. Very nice. Okay.
Thank you very much.
So, yes. So are you going to be in the discussion session?
I unfortunately have a car problem that I need to go and resolve right now.
I see. Yes.
But I might be able to come back later.
Hopefully, yes. But just in case, I mean, okay. So I hope you'll come back because I have.
Okay, I'll try.
Please come back.
Okay.
Okay. So yes.
Okay.
So let's thank
Thank you.
Malcolm again. Thank you very much. Very nice talk. Wonderful.